Santos, and this week's topic we're going to be talking about entropy. So, before we get started, let's take a look at this picture. It's a picture of a kitchen, not my kitchen. My kitchen is actually smaller than this. But on the left side, we have a organized and clean kitchen. On the right, not necessarily dirty, just very disorganized. And for those who do know me, I talk a lot. I talk a lot about this and how messy of a cook I am. So for me, I had to just have all the seasonings out, and everything else that I probably used to cook. So, what is the point of bringing this up? Well, first let's observe or take a look at these pictures, right? Decipher them a little bit better. Um, when I look at them as systems, on the left, my system is organized. Everything is put away. There's not a lot of disorder and not a lot of randomness. When I look at the picture on the right, there's a lot of disorder, a lot of randomness, and things are not put away. So, how does that even decipher into what we're talking about today? So, let me zoom out a little bit. Believe it or not, that's what entropy is. So, entropy is the measure of how disorder or how random a system or how much randomness is in a system. So everything I just talked about in the kitchen, and let's go back to that kitchen real quick. So that means that on the left, um, there's not a lot of randomness, there's not a lot of disorder, therefore it has low entropy. On the right, it's very random. I have so many places I can put these items, right? There's a lot of disorder. It's very chaotic, almost, right? So I would say that my kitchen, after I'm done cooking, would have high entropy. And in order for it to get back to low entropy, I'd actually have to put everything away, right? So let's take a look at the images in here and talk about it a little bit more, right? So when we look at this image right here, we have gas particles. And think back to a classroom, right? Let's say that I had to spray some Febreze, you know, and in the beginning, the particles are compressed inside the can. When I spray it, the particles spread out. And if you guys remember, gases like to take the shape of whatever container or closed container they're in. So in this example, we're talking about a classroom, right? So it goes from inside the container to the shape of the classroom. And if you guys compare both, the gas is compressed into the Febreze can. The particles are wiggling in place, they're moving around, but not so much because it's very limited the space that they have. But once it's sprayed into the classroom, they're going to move around all over the classroom and eventually escape the classroom. That's probably why these smells don't last long, because it's not like it's an airtight room, you know? There's ways that it can escape. So when we talk about entropy, we would say the image on the left has less entropy. So when it was in the can, the gas had less entropy versus when it's out into the classroom, which has high entropy. There's more, these particles move around a lot. If I were to close my eyes real quick, let's say this particle, oh, where'd my pen go? This particle right here, if I close my eyes for a second and I open it again, that particle won't necessarily be there. It might be over here or over here or over here. So it's a lot of randomness, okay? And that's what disorder is. And that's what we're talking about when we say entropy, the measure of just how disordered the system becomes. So when we look at this image down here, we're looking at a brick, like bricks that are laid out. When we're looking at just a stationary setup of bricks, we could say that has very low entropy. There's not a lot of disorder. It's very organized. There's another way to say it. It's very organized. But let's say a car or something pushes it over and they go tumbling everywhere. Now we have more different ways that it can get ordered. So that's a lot of chances or a lot of randomness. And it's very highly disordered. So this has high entropy. Okay. This top brick we know that it's there for this system, right? But then once it gets tumbled over, we don't know if this brick is this one or this one or even this one. So it's, yeah, that would make it chaotic. So that makes it high entropy, okay? And it goes a lot deeper than that. This is just a basic introduction for like an introduction class. So like if you ever take chemistry in college, like a 101, before you get into anything like Gibbs free energy, we just say, hey, just a basic understanding of entropy. This is it right here. And then let's take a look at how that applies to high school chemistry questions. For Regents, we don't really go into Gibbs free energy, but we'll use examples like this, right? So it says KCl, which is a salt, dissolves according to the equation below. So if you guys remember from ionic salts, it ionizes in aqueous solutions, right? So we went from KCl salt to an aqueous solution that has potassium ion and chlorine ion. Okay? So it says the entropy of the system will do what? So if I were to draw this down here, so we have KCl gives me, so we have potassium and chlorine. So if I were to draw this, I'm going to draw K as a circle. And don't mind the colors. It's a rainbow pen, so it's going to change. And so KCl again is the empty, not non-filled in. So we went from 2 circles together to 2 circles separate. So a particle or a compound, right? Because we have 2 elements combined here. Compound broke down to give me 2 elements or 2 ions because this one is charged positively and this one's charged negatively. And if you think about it, there is more order here than there is here. Because this one we're only worrying about one thing or one substance, versus here we're worrying about 2 substances. So there's more ways that I can arrange these 2 than I can arrange just this one particle. This one I can probably arrange it like this or like this, right? Probably even more. This one we could have it like this. We could have it like this. We could have it like this. It goes on and on and on, right? But there's more chaos going here. Or here's another one, really far apart. There's more chaos here than there is here. There's more disorder here than there is here. There's more disorganization here than there is here. Okay, so that means that in this system, because this is the reaction that's happening, and it's not in equilibrium, we're just saying that this is what's happening. Sorry about that. That means that our entropy of the system is going to increase. Okay. Let's take a look at this one. So it says, which 1 mole sample has the least entropy? So this one is talking about, so we went back to this one, and this one's just talking about ionic compound that breaks down, right? Here, we're just talking about chlorine, who's diatomic, right? So it looks like this. Because of the 2, and also it's part of, if you guys remember, Brinkelhoff. And one of the things that is different here is the temperature and the state of matter. If you guys don't recall, the S is solid, L is liquid, the G is gas. Okay, so let's look at those 2 things. So first of all, let's look at the temperature. Remember that when you increase temperature, kinetic energy also increases, right? And kinetic energy is energy of movement. So that means it's moving a lot more. Anything that's moving really, really fast is going to have high entropy, right? This one's asking for least entropy. So it can't be these 2. That's high energy. They're moving super, super fast. Well, the gases anyways. They're moving a lot faster. There's more disorganization happening in these two examples here. But A and B, they're at lower temperature, so they're less disorganized than C and D. But then we're like, okay, same temperature, but then what else is different? So let's look at phase and matter. We have solid, we have liquid. So if you guys remember, when we did particle diagrams, solids don't really move that much. They just kind of vibrate in place, okay? But when we look at liquids, liquids are going to move a little bit more. Those bonds holding them together are breaking, right? So there's more movement going on here. And then eventually, so this is a solid, this is a liquid. And then eventually, as a gas, they're like moving the furthest. They're further apart, they're moving a lot more. There's more energy in a gas phase than it is in a solid. There's more energy in a liquid phase than there is in a solid. And they want least entropy. So that means least energy, least movement, least disorder. So that means it has to be a solid. And that's why we select A. So we select A because it's a solid. So there's less energy, less movement. And temperature, less kinetic energy, less movement. Okay? Less disorder. All right, let's take a look at that. So we have two more. So we have this one which says, which statement describes the equation below? So first of all, we look, they're all gases. So there's not really a change there. But just like the example when we talked about ionic compounds, you can also look at moles here, right? So that's what we're looking at, moles. Here we have 1 mole of oxygen gas. Okay. And here we have 2 moles of hydrogen gas, which forms 2 moles of water plus energy. Okay. So first of all, we have one set, 2 set, 3 set that forms into just 1 and 2. Okay, so we went from a lot of substances to less substances. Still the same amount of particles, it's just that they're put together. Like, so we still have 4 hydrogens on each side, but the combination that created here was we went from 3 diatomic elements to 2 compounds. 3 to 2. Okay, so that means organization is increasing because it's less things. We can say there's less disorder. So we can say that entropy decreases. Okay, but let's look at the first. It's also asking about energy. Is it exothermic or endothermic? And if you guys recall, exo equals exit, right? Energy's leaving the system. Endo means enter. It's entering the system. So for it to enter, it would have to be on the reactant side, or on the left side of the arrow. For it to exit, it would have to be on the right side of the arrow, or the product side. And it's on the product, so that means it's exiting, so it's exothermic. And we look at that combination, exothermic and low entropy. So we can say is B. Exothermic with a decrease in entropy. And the last one. So this one says, given the change of phase, so it goes from water, so ice, because it's a solid, to water gas. So this is phase changes, right? What is happening to the entropy of the system? So again, we go from solid to a gas. Okay, this is disorganized. This is a G, sorry. This is disorganized. They're moving everywhere. If you close your eyes, particles won't be in the same location. More chaotic. So that means this has high entropy, okay? It increases. So as we go from a solid to the gas, entropy increases, but when you go from a gas to solid, it decreases. So since they're saying what happens as it goes from a solid to gas, you can say that entropy increases. Okay, I hope that makes sense. Just remember, entropy doesn't just apply to chemistry, it applies to life. Like right now, as I record this video, my hair has high entropy, meaning my hair is a hot mess. And again, entropy describes many things. And I hope you enjoyed this lesson. And if you have any questions, just leave me a comment or reach out to me. Have a great day.